Hi everyone, my name is Saad Sadiq and I'm from the ECE, and my research is on AI and deep learning. And today I'm going to talk about one of our papers, which is to identify faces and adversarial rare events when somebody is trying to fool us. So rare event detection is more relevant than ever. More and more applications are using your face identification, and your phones are now in the game. IoT devices and mobile devices are in the phone. Now they need to be real time. They need to detect everyone, and they need to identify those blacklisted rare event outliers that are problematic. Well, it's really hard to do it on conventional mobile devices. If you want to run state-of-the-art face identification software, you need a heat sink at the side of a Rubik's Cube on your phone to cool down your phone if you want to run state-of-the-art deep AI. So what you do is, this is Jacques Chirac. He's from France. So what you do is you take landmarks, get his face, rotate, shift, scale, and then get the features, and then identify every single image in the repository to the detected face. This is unfortunately the fastest one and most efficient one, not the most effective one, but every face in the repository. So as face identification come the adversarial attacks. People try to fool the classifier by doing makeup and adding pieces to their nose and chins, but that's not what they fooled us. This is what fools this. These are iteratively trained over hundreds of thousands of adversarial training samples that trains the deep AI software to identify those artifacts that can fool the classifier. So this is what we are targeting to avoid. So what we did, we train our own adversarial faces. We take our faces, we put them in something called GAN. It's called Generative Adversarial Nets. What it does is, it will take our faces, merge them with a noise vector, and generate new faces that will try to confuse the discriminator or the classifier. It usually identifies my face very well, but added noise, it will either say yes or no. But we want to say 0.5, I don't know. That's what we're targeting. Those are the images that fools the classifier. And we got, surprisingly, those strange images. But these are the adversarial images that fool the classifier. So IBM Watson has one of the most accurate face classifiers on the market. It takes 20 images to predict a good classifier. We take anywhere from 2 to 5 images, and we create generative adversarial images that can complement that lack of samples. So what we do, we take a 640 by 480 very low quality camera at 24 frames per second on a small 9-volt mobile kit. And then we capture the face, align, crop, rotate, and then we take the landmark so we can fuse it with the adversarial images. This is our CNN that we made. It's a reduced CNN that can run on low power devices. Get the features, fuse the GANs, and then identify the faces which we are trying to get. So this was done at the time of Parkland shootings. So our idea was that every school CCTV camera should have a small mobile device attached, embedded to the camera. As soon as suspects walks in the school, the CCTV camera should do the job, not any human sitting behind the camera. So this is NVIDIA TX2 board. This is a GPU, CPU, RAM, ALU, everything on a single board that can fit in the palm of my hand, size of a credit card. So what we did is we implemented it, and we can achieve like several power modes based on what's the inflow of students walking in the school in any public environment. I can adjust the performance based on the load. And as you can see, the power watt-hour rating was, as compared to the state-of-the-art, since it's a 9-volt powered system, it's only 7.6 watt-hour. And the accuracy, as compared to the state-of-the-art face identifiers, is really up there. So we were able to achieve good accuracy with low power that can be implemented on a device at the side of a credit card. Thank you.
Hello everyone, my name is Bushra. I'm a PhD student in Industrial Engineering Department. So today I'm going to talk about the role of data analytics in operations research and management sites. So what we do in operations research, we study problems, industry-related problems, business-related problems, government-related problems. We use mathematical methods to observe, explain what we observed, make decisions, and propose solutions to improve the current state. But the way that we approach the problem is highly theoretical. We have complex mathematical equations, and we have assumptions, and their proofs, proposition, and etc. And today, there is this growing attention on data analytics. But actually, it's been almost 20 years that everyone is talking on data, so it's not something new. But what is new for the operations research? They are under threat of being left behind because industry outside, many businesses, like e-commerce, for example, they are saving billions of dollars, even with simple algorithms that they come up with. So it's not just the money, because they have an access data, they manage the risk with using data techniques, and then they improve their current system. And then they're discovering the facts that academic research did not know before. So if you want to look at the quickly past 10 years, so in 2009, one of the biggest society operations research ran a worldwide survey, and then we wanted to question where the current practice OR is. So the results were remarkable because for the OR jobs, advanced mathematical workers were not required. It was okay for them if they do simple statistics reporting and if they know the organizational culture. Of course, it was a hit for the academic research in operations society. And in 2011, they said the practitioners from the United States, the scholars, what are you guys simply doing there? We have an access data, we are saving billions of dollars, and then we need your help because you have the ability of critical and analytical thinking. But they were still competing on the data analytics. And then demand analytics was born. They were mastered on forecasting. In 2013, two biggest society regarding operations research, one in the United Kingdom, one in the United States, they merged together to promote science for better, which means that they will voluntarily to help the industry. And then data analytics was born because operations research is not interested in too much using data for simple reporting and statistics. They are interested in to use data for decision makings. How can create a decision model which is data supported? That's why they come up with this fancy word, decision analytics. And in 2015, another big society ran a survey because they wanted to last time make sure that where they are heading is accurate and then applicable for everyone. And since then, industry is competing on decision analytics, especially in healthcare settings. And then right now, academic society are calling scholars for special issues on this topic. So for the sake of my research, what I do, I bring this methodology, which is, with of course the help of my advisors. So we start with an idea, especially in operations, this idea must be very, very complex, target complex problems. It's not a stage where we are asking whether or not this variable is statistically significant for outcome, because these are going to be answered by fact-based management, next steps. Because if we target a complex problem, we can answer why did it happen, how it happened, when it happened, how many times it happened. And then we can use factor analysis, significant, like correlation data, days of visualization, descriptive and diagnosis, all the things, all the data tools are embedded in this section. And then once we want to predict something or doing some algorithms, writing on some algorithms for decision making, we need to be perfectionists. Because we use the statistical inference, data fitting, all artificial intelligence algorithms, collaborating, filtering. So this is the methodology that I follow. And in my dissertation, my dissertation title is The Business Model and Data Analytics for Complex Service Environments. You can name as hospitals, you can name as construction sites, you can name as heavy maintenance industries. In fact, I have an actual data from a maintenance industry that does, in the United States, that does maintenance for aircraft, for the aviation industry. So the problem is, the orders coming in, and then it's unknown how long they will stay in the system. And it's unknown also how well the service provider performs at the same time. But I can explain all these with the available data. What I have capacity, I have labor hours, I have order characteristics, customer ID, and all stuff. So what I do is basically using all the metrics, map them, writing algorithms, prediction, fitting, and that's all.
Thank you.
Hello, ladies and gentlemen. I am RDF Fakul from Electrical and Computer Engineering, and I am a PhD student. My research is gender recognition on surveillance video, and today I will present it. Although there are a lot of gender recognition methods in the literature, they mostly based on face images or still images. They don't use the all person information, or they don't use the video in their works. Our works focus on video, and we focus on the whole information from person. We are using deep learning, especially two different convolutional neural networks to process data. We are using convolutional neural network, CNN, and recurrent neural network, RNN. The CNN consists of two different elements, the convolution layer, which are feature acceptor. Basically, you feed the image or your data to convolution layer, and a stack of convolution layer gives you the image features. And the other one is full connected layer, which is responsible to classify the features, which are decision-making layers. And I'm using recurrent neural networks, RNN, because they have the memory, and because of that, they are suitable to process sequential data like video. We are using CNN model, the convolutional neural network model, to process images, and recurrent neural network models to process video. In CNN experiments, we trained more than 10 famous, well-known CNN architectures, and some of them are listed in the table. And we found that ResNet version 101 is has the best performance in our surveillance video, gender detection from surveillance video case. In addition to that, in RNN experiments, we combined convolutional neural networks with recurrent neural networks. We add the recurrent neural networks to carry the image feature in time, and at the end of the sequence, we get the decision from full connected layer. And we found that the accuracy of, although we found that the accuracy of the recurrent neural network model, the combined model, is approximately the same with the CNN model, it is only preliminary results, and our goal is develop that model and achieve a better result, and we believe that that model will be better with more training and more work. In addition to all of those, according to literature, the gender recognition from face works better with respect to gender recognition from body. But we found that if your input image is surveillance video, then gender recognition from body is more informative, and it's 10% more accurate than gender recognition from face. To summarize, our goal is build a model to detect gender from video instead of detect gender from images. We build a model which consists of convolutional neural networks and recurrent neural networks, and our goal is achieve a better performance with that combined model with respect to convolutional neural network model. Thank you.
Okay. Good morning, everyone, and thank you all for being here. By means of a brief introduction, my name is Nurçin Çelik, and I'm an associate professor in the Department of Industrial Engineering. And this work is actually relatively a new research area for us that we are very excited about. And the part that I'm going to be presenting you today pertaining to our research interests, but this is a part of a bigger initiative that goes across multiple universities as well as multiple research domains, including cell and molecular level experiments. So if I may, let me see. There was actually supposed to be a video, a short animation here, but because it's a PDF, it doesn't run. What happens is the cells, they start on top of the hill, and as they go through these valleys and different stages of the epigenetic impacts, the way that they function changes, similar to the DNA's operation. And all of this is actually called the epigenetics. So by definition, the epigenetic refers to all of the heritable alterations that occur in the gene function without a change in the actual DNA sequence. So as part of this epigenetics reasoning, the DNA methylation has a particular interest to us, and mostly because it's getting impacted a lot about these epigenetic changes, and also it may have a devastating impact, such as diseases, including cancer. So we know that the cancer is associated with the levels of the methylation around these DNAs. As you can see on the right-hand side of the slide, the normal cells usually have relatively low or normal levels of DNA methylation, whereas the cancerous cells, significant levels of DNA methylation around them. So we also know that some parts of the DNA is being silenced because of these methylation levels. So basically, it's inactivating the part of that DNA sequence without having any impact in the actual DNA sequence. So basically, the environmental impact is associated with the function of this DNA. However, the profiling of this DNA methylation is not an easy task, mostly because of the size of the data. We are dealing with a very big data sets, as well as high throughput data. Just to give you an idea, the data set that we are dealing with has 485,000 attributes alone, and this is just one data set. And so in order to address this larger problem of how to handle high throughput data in the DNA methylation profiling technology, we are going back and forward about different DNA data analytic techniques so that we can actually come up with better accuracies without losing from the speed or the computational savings. And it's going to hopefully help us tailor some of the related treatments for these cancer and other diseases one day. So in terms of our specific contributions to this problem, comes actually twofold. We have contributions published in the unsupervised learning as well as the supervised learning aspects. In terms of the unsupervised learning, we have developed 3 algorithms: variance-based dimension reduction algorithm, outlier detection algorithm, and taboo-based clustering algorithms. So what we are basically trying to do is, in an unsupervised setting, can we cluster within this DNA sequence, can we cluster the parts that has the largest levels of DNA methylation so that we can identify them as tumorous cells as well. And in the contributions as part of the supervised learning, we are targeting more on the maximum relevance and minimum redundancy so that these clusters that we came up with are actually meaningful clusters. And for this, we have developed a brand new feature selection algorithm incorporating some of the traditional aspects and also some novel aspects as well. And when we compared our work against the traditional works, what we did for the unsupervised learning was basically a dimension reduction algorithm. So we took that and then we incorporated it into the traditional algorithm, and then we took the traditional algorithm alone and then compared them. We also did the same thing with our feature selection algorithm to see how much of a benefit we can have at the end of this running. And the results actually, the results have shown that the performance of the hierarchical clustering algorithm, which is a very traditional unsupervised algorithm, and k-means with our outlier detection algorithm, we were able to show on average about a 20% better performance in terms of the accuracy in the way that they are clustering. And also we were able to show that, you don't see it here, but we were able to show that we are not losing much from the computational speed either. And on the right-hand side, you can see some of our preliminary results on how we are clustering them. And if you have any questions, you can reach me out in the Department of Industrial Engineering. So thank you very much.
Hi everyone, so I'm going to talk about a small project, collaborative project with NREL. So the project is an anomaly detection using a Bayesian hierarchical structure for wind turbines. So as you know, most mechanical systems are subject to different types of anomalies and abnormal behavior, and the idea is being able to use sensor measurements to detect these anomalies, because it's impossible to just look at the system and say if the system is working under normal condition or not. So the main contribution of the work is, because we're dealing with very large data set, we just want to make sure that we only use the important samples in the training data, right? So we are only focusing on the samples that are effective and important, and also only on the important set of features, right? So these are the main objective of this work. At the same time, we just want to make sure that the outcome of the data analytics can be used for decision making. That's why we consider the trade-off between detecting anomalies and also the false alarms. So because depending on the applications, this trade-off can change. So if you think of a simple response model, so we can model the response of the system here as y based on a nonlinear transformation of the inputs of the system plus some noise. So I can talk maybe 2 hours just about how we do this nonlinear transformation, but the idea here is that we use past data to be able to train that. And now there are two main elements in the system. So I don't want to bore you with this equation, but the idea here is to define some variables that can tell us simultaneously what are the important attributes in the data set and what are the important samples, right? So we are using a hierarchical Bayesian structure which gives us the ability to interpret the model better. So it's highly interpretable, and also we can control the model complexity using some hyperparameters. Now, this is the main part for the decision making. So the decision makers now have the ability to define the trade-off between detecting the true anomalies versus minimizing the false alarms, right? And based on that, we developed this decision-making model, and then we end up getting a simple control policy. Basically, we transform the set of sensor measurements to some nonlinear function. We compare it with the threshold. If they're above or below those thresholds, we can say that the system is under anomaly conditions. And we are doing it for both supervised and unsupervised setting, meaning that we can identify also anomalies that we have not seen before in the system, right? So this is the structure. We of course do the training first, and then after the model is trained, we do the actual anomaly detection. Now this is a data set that actually I can present. This is based on real data sets for wind turbines. So the inputs are typical SCADA measurements such as wind speed, direction, and temperature. And the main outcome here is the power generated, right? So the idea is to be able to look at these measurements at a time and see if the turbine is working under an anomaly condition. And we see the first outcome of this work is we can see that we can predict the actual power generated under normal behavior model using our models, and it works pretty well. And you can see that the predicted values are very close to the actual values. This is one of the main outcomes of this work. You can see all these points. This is a typical S-curve wind speed versus power generated, right? And all these points are the points in the training set, just a subset of points. And you can see those red points are the points that are actually selected finally as effective sample points. When you're dealing with a large scale data set, you don't really have to use all those points. And again, remember, these points are selected by the model, right? So we are basically decreasing the size of the training set, which is an important factor for computational purposes. And then at the same time, we are only using a small subset of our attributes. Not all attributes are useful to be able for this kind of anomaly detection. And again, I didn't have time to explain that. We are, of course, using MCMC to first use historical data to train this model, and then after the model is trained, then we can use that for testing. And we use some kind of parallel computing, making sure that we can run this very fast. And also, if we compare this with one of the state-of-the-art models for anomaly detection, we can see that the risk is lower. And again, the ability of the decision makers here to define the trade-off between false alarm and detection rate is an important factor of this research. And we can see that we can have less false alarm and also less lower risk. And also the decision maker can define different thresholds, and based on the threshold they can decide to finally generate an alarm for the system. And this is up to the trade-off again between the true detection rate and the false alarm. And in future work we are studying some high leverage data point and oversample and undersamples data.
Hi everyone, I'm Jie Xu I'm an assistant professor from ECE. I'm going to talk about this project, Security Aware Incentive Design for Cooperative Networks. And this project is supposed to be game theoretical, but I'm not going to show you any equation today in light of time. Rather, I'll be focusing on the motivations and the general framework. So the way functioning of many networks relies on various levels of coordinated behaviors of its users. For example, in mobile ad hoc networks, users can forward traffic for other users. In cooperative sensing, users can share their sensing results to improve their sensing accuracy. In all these so-called cooperative networks, undertaking these cooperative actions is actually costly, for example, transmission energy consumption, but it brings no immediate benefits to the users who provide the cooperative service. So absent incentives, these users, selfish users, will be unwilling to cooperate. Thus, these networks may fail to work. So a central theme of this literature on cooperative networks is the design of incentive mechanisms to promote cooperation and thereby achieving specific network level objectives. So actually, there's a variety of incentive mechanisms already proposed in the literature. I'm not going into detail, but despite the different forms, the key idea is really similar. So basically, the users have to obtain satisfactory benefits that can at least compensate for their cooperation costs, right? So users are they are determining their cooperation action or the cooperative effort level based on a careful benefit cost evaluation, right? So in the traditional incentive mechanism design, they consider costs that only depend on users' own action. So it doesn't depend on the other users' cooperative actions. For example, energy consumption, it depends on how much traffic a user is willing to forward for others. But the security cost is really quite different from conventional costs, because security risk is often interdependent among the users, and security cost is really a result of the collective behavior of all network users. So without fully understanding how these interdependent security risks emerge in cooperative networks, how they shape user incentives, and how do they affect the eventual incentive mechanism design, simply applying existing solutions can lead to great performance loss or even damage to both individual users as well as the overall network. Okay. So in this project, we try to tackle this security-aware incentive mechanism problem, and we propose a general framework, and in particular, we formulate a novel Staggerberg game with one leader and multiple followers. So in this Staggerberg game, the network designer will play as a leader who will design the incentive mechanism. For example, if a mechanism is payment-based, then the designer can design the payment function. And the users, there are multiple users, they will play as followers, and they're going to choose their cooperative actions or cooperative effort levels. But different from conventional Staggerberg game, the users are not only playing best response to the leaders, which is a network designer's move, but also they're playing another game among themselves because of the interdependent security risk. So here we are really solving two coupled games at different levels. Okay. So another issue in this framework is how do we model the interdependent security risk? Right now we are focusing on epidemic models. So for example, the self-replication malicious codes can be inserted into the data exchanged in the cooperative process. So a user can be compromised if it chooses to cooperate. And furthermore, the user becomes a new source of attack when it interacts with other users in the future. So the security risk can propagate across the network. Right. Now, in light of time, I just show you one result for a specific case. So we're starting a random mixing-based epidemic model. And I call this result a more or less result. And also here, the designer is using a payment-based incentive mechanism. So here, we can show that if you increase reward provided to the users, it promotes cooperation, which is kind of intuitive. But surprisingly, on the other hand, too much reward can also harm the overall network performance. And the reason is, if you have too much cooperation, then it can potentially foster persistent epidemics, which is a risk in the network. So basically, we want to show security-aware incentive design is very different from the traditional incentive design. And we have to, consider all these different features here. Thank you very much.
Good morning, everyone. So I'm going to talk about my research. My research is in two areas. First area is data analytics, and another one is application of data analytics to bioinformatics problem. So, but here, obviously, I'm going to talk about the research in data analytics. So I'm going to talk two pieces of my recent work. The first one we call a semi-supervised classification. So now, suppose a patient, let's say, as example, a patient undergoes a surgery and doctor remove let's say something like a tumor. Then the next step would send some samples of this tumor to a pathological lab to determine if this is a benign or a real tumor, right? So the traditional way is that doctor, gets samples, examines the tissue under the scope, microscope, to determine if it's a benign or a tumor. But now, more recently, researchers are developing this method using molecular signature, or more specifically using expression level of thousands of genes to determine if this is a real tumor. So now, if we use gene expression, we have thousands of genes. Right? We have basically we need to develop a computational algorithm we call the classify to do the job to classify this is a tumor or benign tissues. So this is a challenging problem. We have thousands of features, and also we want to use some we call the labeled data. We know this is already a tumor or benign tissue, or we have also some unlabeled data. We don't have any label. We don't know it's a tumor or benign tissue. So then we developed an algorithm called the semi-supervised sparse logistic regression algorithm. We form an optimization problem. This problem object function is a non-convex, non-smooth function. But anyway, we developed an algorithm, and we apply this algorithm to several data sets, and then our algorithm performance on the top is the best performance. This result is in a paper we submit to a journal. It's under review. And then I want to spend maybe 2 more minutes on another work called gene network inference. We know expression of a gene is one gene is regulated by other genes. For example, in the picture there, one gene in the beginning of this gene, there are 5 binding sites of other genes. When other gene binding to this binding site, so they are going to activate or suppress expression of this gene. So genes, they are intact, form extensive network. So now if we have expression level of genes, for example, this Y of thousands of genes, we want to infer the structure of this gene, this gene network. So also we want to use some information in the DNA sequence we call UEQTL. So this X, so the goal here is infer the gene network structure. So now we form a mathematical model called structural equation model. So Y of gene J is regulated by other genes and also affected by we call the EQTL. So we form a structural equation model. And now this model, the unknown parameter in this model is B. This B matrix can be thousand by thousand matrix. It's a big matrix, have millions of variables there. But what we know about this matrix is this matrix is sparse, which means although we don't know which number is non-zero, but we know there's a lot of zero in this matrix. So using this property, we form what happened? I don't know what happened. Suppose there's something. But anyway, we form a optimization problem again. This optimization problem have millions of variables, and as non-smooth, non-convex, we develop an algorithm, and we estimate the gene network, and we compare the performance of this method with other state of other method. We get the best performance. So I guess that's all.
Hello, good morning. I'm going to talk a little bit about some of the research I've been doing for a few years. It's about extracting information from imperfect data. So I'll try to sort of motivate the problem and try to get through the 50 slides I have. So, all right. So we know that the recent growth of AI and ML technologies is unprecedented. In fact, this has given rise to enormous transformations in how people make decisions. For example, deep learning and other techniques are now almost routinely used in a lot of the machine learning algorithms. But what we must realize is that the practical utility and the effectiveness of almost all these algorithms depend on how well we can actually learn the parameters. And these parameters are learned from training data. Right? So that's the first thing. The problem, of course, is that the representative statistical training data are often unavailable. For example, there are reasons for that. One is cost, could be in terms of time or effort for getting adequate data, or it's difficulty getting data for infrequent events, rare events, or sometimes you are not given the data because of security and privacy concerns, right, in medical data, for example. Another thing is data imperfections are pervasive in real world data, although you may not realize this, the data sets that are available to you are already cleaned, or sometimes the data is you are only given the clean data, right? So you have in true data sets you have missing data and ambiguous data and things like that. So the question is, how do we proceed with such dirty data and actually extract information? So one of the strategies you might think is okay. Let's just use only the clean data, right? So any dirty data records that you have, you just throw it out and try to learn the parameters from dirty data. So I'm going to claim here that that particular procedure is inherently flawed. So here we have a very simple example of 7 data records, and each data record has 3 attributes, A, B, and C. And let's assume that A, B, and C can take 2 values. So A can take A1 and B1, A1 and A2, and B can take B1 and B2, and so on and so forth. So if this is the set of 7 data records, and these squares indicate missing values, missing data that is not provided to you. So from this you can actually figure out, you can estimate the probability of A1, B1, and C1 occurring. So there's the problem being that you don't have these data, you cannot actually figure out the exact probability. What you can get is probabilities, upper and lower bounds. So if you do this for this particular data set, believe me, you get between 1/7 and 3/7. Those are the values you get, right? So I don't care what values you put inside the squares. You should get a value between 1/7 and 3/7. There's no way you can get out of that. So if you pick one value from 1/7 and 3/7, you are essentially picking one imputation strategy. That's essentially what you're doing. On the other hand, if you ignore the dirty records, in this particular case, there are only 2 clean records, I think these 2. You can see the probability of A1, B1, C1 is half. And half is outside that interval, right? So this is 1/7 and 3/7, half is outside. So which basically means no imputation strategy can give this value. So this very simple example illustrates that ignoring dirty data records is inherently flawed. I mean, you cannot use it. Right? So simply ignoring the dirty data records and learning the parameters from clean records is not right. You get wrong results. So next one, here we go. So the other strategy is, of course, use the imputation model. So which is sometimes referred to as a missingness model. So if data missingness, if a model is available, you can use this model to actually fill in the missing data or correct the wrong data. But usually the problem is there's inadequate information to justify the assumptions that you to arrive at a missingness model, right? So what we need are models that make little or no unjustifiable assumptions and are better equipped to capture other types of data. Why do we need other types of data? Because when you don't have enough information, you want to get information, information from all types of data that are available. In particular, human-generated soft data. So, for example, if an expert makes a statement regarding, I am 80% certain that regimen A works, then you want to be able to model that. I claim that this is difficult to it is difficult to model this using probability models. Number 2, nuances in natural language statements. If somebody says, I don't think regimen B would work on a particular patient, how do you model that? Right? So these are natural language statements where modeling is not easy. Imperfect implications. For example, you can have implication. I mean, people use rules all the time. So if you have imperfect implications, it's not possible. For example, smoking implies blood pressure. There's an imperfection here. So how do you use that? So that's basically the research that I'm doing. Thank you.
Hello. I promise I have no equations. So the challenge, what are we trying to do? There's a lot of data, big data. We're in the era of big data. Challenges, can we get the true signal values from the noise, track evolution, discern outliers, and ultimately obtain knowledge? There is an emerging approach, particularly in signal processing and some parts of machine learning, to connect similar data streams through network structures. So you say the edges in a network represent the similarities and influence between the data streams, and the nodes are essentially the data streams. And so what you do is you use a network structure together with signal processing and tracking and machine learning to make sense of the data. There are lots of applications. For example, online social networks. How do you discern the formation of opinion clusters among groups of individuals? This is of particular interest for understanding, how ideas form and evolve in societies. Cybersecurity, how do you estimate the network state and detect a cluster of compromised nodes? And in general, anything where you have multiple time series, so you have geophysical sensor data, the stock market, you can all start putting network structures together with the time series to make sense of the data. A lot of these applications, our focus has been on non-stationary statistics. So you have evolving situations where the statistics are not stationary, which means that things like deep learning may be problematic here. But you have fads, malicious users, seasonal effects, things that are constantly changing. The network is time varying, so friendships could change, certain nodes gain influence, etc. Sensors go offline, some new sensors come in. And so what we do is we look at an analytical problem that captures all this, and so our work is more theoretical. These problems are basically modeled as extracting information from noisy, non-stationary signals and data emanating from time-varying networks. So we will focus on some fundamental work on this topic. What do? We use adaptation and learning to handle the evolving nature of the signals, data networks. We focus on scalable solutions. The idea is that if you have millions of nodes, you should be able to get algorithms that can handle that case. We've been using statistical signal processing and machine learning to do things like dimensionality reduction, convert high-dimensional data to low-dimensional data, distributed solutions, so you don't have to have centralized data in one spot. You can have it on parallel clusters or other types of message passing solutions. Data reduction, I don't want to look at all the nodes in the network, I want to look at some of them. So just to give you some pictures of what we've done, and the grad student who's done this work is in the audience. You can ask her, Maysar Lin. She looked at a time-varying network, and what she did is came up with a distributed adaptive tracking of signals in time-varying networks. So the network is changing, the links attributes can be changing, or new links can be forming, and edges can be dropping off. For this particular case, and then the signals themselves have non-stationary statistics. So they were following a random walk model, and she came up with adaptive, learning algorithms. And the dotted lines show the fundamental theoretical performance limits of the algorithm. So she's showing that we have an analytical characterization of performance of the algorithm. That's important for a lot of learning tasks, because right now, people are caught up with deep learning, but we often don't know why does it learn, why did it do what it did. Here we are focusing on, can we characterize using analytical performance analysis what the performance limit of the system is going to be. And so the dotted lines predict the performance of the mean squared error over time. We have this also for time-varying networks as well. I'm not going to show you the picture. Now, the additional question, suppose I want to estimate the signal that is evolving over time in a time-varying network, but suppose there are outliers and also additive outliers. Someone is injecting malicious data. So suppose I have something like this. In addition to this, within the same estimation problem, we came up with a method for estimating the outliers. So each node is trying to estimate its own outliers. And so you can see for two of those black cases, the black dots are the outliers. You can see that the red line is our estimate of what the true outlier is. And so we have some analytical performance characterizations of this work, and we're also now working on the detection capability. How do you actually form a detection based on this? The last thing is data reduction. Okay, go back to this. Suppose I have 1 million nodes. I don't want to work on 1 million nodes. I want to work only on a few nodes, a fraction. So how do you do that? Well, this is a big problem right now in signal processing machine learning. It's called sensor subset selection, sensor selection. I only want to use a few sensors to figure out what's happening in the whole thing. This has applications to the Internet of Things, because you have lots of devices are going to get sensors, and they're going to be reporting the performance. You want to use only a snapshot. You want to get a snapshot from a few of them. So we came up with an algorithm that you can use only a small percentage of nodes, and it actually performs better than comparable algorithms developed by other people who are using different programs, different methods in signal processing. But what's actually I'm not showing is the complexity reduction. Our algorithm is actually O of n cubed versus O of n to the fourth, which for the other ones, so it's, in terms of complexity, it's a much faster algorithm. And so, anyway, that's all. Our work provides a framework for making sense of data from networks using signal processing, machine learning, and network science. That's all.